Hello everyone, we are the research group of Associate Professor Junping Geng, Department of Electronics Engineering, Shanghai Jiao Tong University. My name is Jing Zhang. Today, we will introduce a dual-port phase antenna and its application in 1D arrays to 2D scanning. We mainly want to solve two key problems. First, the traditional antenna element has a fixed radiation mode, which limits its role in beam scanning. Second, based on the traditional principle of pattern multiplication, 1D linear arrays are difficult to achieve 2D scanning. To solve the above problems, we designed a dual-port phase antenna based on SSPPS. The proposed antenna consists of three parts, two monopoles, an SSPPS structure, and a ground made of aluminum. Port 1 and Port 2 are fed with M signals with same amplitude and different phases. The phase difference between the two ports, delta phi, equals phi 2 minus phi 1. 3D patterns varying with delta phi are shown here. Distinctly, as the phase difference delta phi changes, the radiation patterns realize 2D scanning in 1/8 of the sphere space, where x is greater than 0, y is greater than 0, and z is greater than 0. Based on the generalized principle of pattern multiplication in phi theta space, we construct a quaternary generalized linear array. The phase difference tau can adjust the generalized array factor, which can only be scanned along the theta direction. The phase difference delta phi between the dual ports of each antenna element remains the same, which can be scanned not only along the theta direction, but also along the phi direction. By simultaneously regulating tau and delta phi, the 1D generalized array can realize 2D scanning. Based on GPPM and phase antenna element, we construct two quaternary linear arrays. These two linear arrays can achieve high-gain scanning along the directions of theta and phi simultaneously. Experiments have been completed and the excellent performance has been verified. That's all. Thank you for watching. For more details, please click the DOI in the page.
This video would introduce our work about dual processed one-again scanning phased array antenna for 5G communication system, which is published on XIII translation antennas and propagation. I would like to first thank the editors of the journal and the reviewers for their contributions to this work. I will present this work from three aspects: design, per simple antenna designs, and performance. For example, as shown in Figure 1, the patch antenna only excited the horizontal current on the patch, and the adjacent unit also induced the horizontal current, resulting in strong coupling. To weak this coupling, we introduced a vertical current through the band radiation patch, as shown in Figure 1b. This will generate both horizontal and vertical current. The adjacent bending arms will induce the vertical current between the vertical arms. When this part of the current is transmitted to the horizontal patch, it will be opposite to the direction of the horizontal current induced from the horizontal patch, resulting in a cancellation effect on the patch. However, the vertical current is weak, so we connect the two vertical arms together to enhance the current constellations. Therefore, the good decoupling effect can be achieved. It has the similar function in the H-plane as shown in Figure 2b. This method can not only achieve the cancellation effect but also improve the antenna radiation performance. As shown in Figure 3, the vertical current has the EM wave to radiation to both sides of the tunnel, thereby broadening the beam tunnel radiation patches. Designs as shown in Figure 4 is the configuration of the proposed tunnel. To highlight the proposed work, two reference the tunnel are given as shown in Figure 5 to compare with our work. The mutual coupling and the radiation pattern as shown in Figure 6 and Figure 7. The proposed method is proposed by these results. 4x8 planar real tunnel is fabricated as shown in Figure 8. The character distribution of the planar array antenna is shown in Figure 9. We can find the weakened induced character is on the adjacent unit. Hence, it can achieve a good radiation performance as shown in this picture, which is measured in the alcohol chamber as shown in Figure 10. Conclusion, a simple and efficient method is placed to realize a propelled dual polarization planar array antenna is low mutual coupling and wide-angle scanning capability. Thank you very much for watching.
Hello everyone, this is a share of paper titled Wideband Wide-Angle Scanning Phase Array based on miniaturized metal surface antenna. With the development of wireless system, phase array antenna is required to realize wideband, wide beam scanning properties and be planar at the same time. Due to nonlinear dispersion of metal surface antenna can achieve wide bandwidth while remaining advantages of microstrip antenna. So, applying the metal surface antenna in wideband phase array is a good idea. However, the problem is that the size of wideband metal surface antenna is too large to avoid high side lobe, or bandwidth is reduced with size reduction. This is the design process of this paper. Firstly, the dispersion characteristic of metal surface unit cell is analyzed. When the width of two types metal surface unit cell changes, the unchanged dispersion curves was found in the metal surface of rectangular patch without wire. This property is utilized to reduce the metal surface size in each plane. In addition, a high slope property of dispersion curve is presented in this metal surface, which means that the phase shift of this metal surface is equal to pi over a wide frequency band and indicates a potential wideband performance of this metal surface antenna. This property is utilized to reduce the metal surface size in E-plane. By combining these two properties, a miniaturized metal surface antenna is achieved. Wide bandwidth of around 30% and its radiating size is reduced to 0.38 by 0.42 wavelengths. The microstrip line is modified to strip line to avoid the backward radiation in planar phase array. For infinite array, plus and minus 16 degrees beam scanning range with about 22% bandwidth is achieved. This is fabricated 8x8 metal surface phase array prototype. Both the bandwidth and half-hour beam width of central element are wide. Based on the far-field scanning patterns of the 8x8 metal surface phase array, good wideband wide-angle scanning performance is achieved. No grating lobe is paired, and the side lobe levels are less than minus 8.7 dB within the 16 degrees beam scanning across the entire operation frequency band. A summary of this paper is presented here. That's all. Thank you.